Hello and welcome to the presentation of the electromagnetic workbench in the freecad users conference. First of all, let me thank the organizers for giving us the opportunity to speak about our workbench in this conference. Who we are, we actually distribute open source solvers for electromagnetic problems since more than 20 years. We usually start from some project that has been developed by some university that mainly is MIT, and the code has been distributed in open source and it stays that way. That's also our mission. And we provide all the support, customization, fixes, as well all the tools that are needed to make it easy if you want to use those solvers. The solver we distribute, and also our name is well known if you want in the environment, so you can look up in Google Scholar fastfieldsolvers and you get more than 200 papers citing us. You can also check the name of one of the main solver, which is FastHenry, and see that you get more than 2,000 results. So there's more than 2,000 papers that has a FastHenry as a citation. Of course, that goes to the credit, of course, of the original authors, but we played, I believe, an important role also in making those solvers available and usable. What we distribute, which kind of software we distribute. So there's a class of solver which are used to extract the capacitance in 2D and 3D. So mainly you're deriving a capacitor, okay, or a capacitance. That's very useful if you have to characterize packages like IC packages, or maybe if you're working with touch panels, you're working with the ICs and so on and so forth. So there are really a large class of problems you can address. That's just an example. There's another class of extractor that works instead in the magnetic field. That's for extracting 3D inductance and resistance. So mainly you extract a resistor and inductor, or if you want a mesh of them. The usage mainly is for power electronics, of course, for, again, characterization of packages or low frequency calls, etc. That class of extractors work in the low frequency domain. So they're so-called magneto-quasi-static or electromagnetic or electro-quasi-static extractors. Means that you don't have field propagation, you don't have antennas, just to be clear. We also support another extractor, which is a full 3D full wave extractor that's called FastImp. This one you can use for higher frequency. So you can, for instance, design RFIDs, so the codes that are used for tagging, I don't know, the shirt that you buy in the different shops, and automatically you can see the price. Okay, so all those softwares are developed in open source, so you can see the code, you can proof check the algorithm which is behind, but they have a cons. The problem is that they're, if you want just a solver, right? So if you look, for instance, at the FastHenry input format example here, just like in this file, this is a text file by which you need to define all the parameters, mainly the geometry, as well as, of course, all the parameters that are needed for the simulation, just like the units or the type of material and so on and so forth. So this is not very friendly, if you want. So you can create, for sure, manually this file. If you have a complex geometry, you may use a script, but not very user-friendly, right? So we developed, actually, the electromagnetic workbench for freecad. Point is, our task is not to develop a CAD software. So actually, freecad is much better choice than anything else we could develop in that respect. We are interested, if you want, in the solution part. And so freecad was perfect as a choice, as a front end for the field solvers we distribute. So the electromagnetic workbench is available as an add-on, is a workbench, is downloaded from within freecad. It has a FastHenry interface fully up and running. That means you can extract inductance and resistance. There's also a VoxHenry interface in beta. What is VoxHenry? Is again an extractor for inductance and resistance, but based on voxels. What are voxels? So the basic element with which you work is a block, is a cube, is a voxel. Voxel is the 3D equivalent of a pixel. If you ever played Minecraft, you know what a voxel is. I mean, the block in Minecraft is actually voxel. And also there's support for faster cap and fast cap, which are the capacitance extractors via some scripts. So that's not fully developed at the moment. So we'll see in the next to come, if you want, evolution of the workbench. So let's now have a, if you want, a short review on how to install. Of course, having the solvers is a precondition for using the workbench. So you may use the workbench without the solvers, but okay, you just generate a text file, which is not very useful for anything else. So first of all, we recommend that you download and install the solvers. On Windows, you can do that by downloading the fastfieldsolvers bundle from our website and install the bundle. Very simple. On Linux, there's not a bundle. You can download the sources and compile them on your own. You still find the link on our website. There's also some pre-compiled binaries for some Linux distribution on wrcad.com. And you can also download FasterCap, which is our own solver from fastfieldsolvers, if you're interested. And then you can install the workbench as usual within freecad from Tools Add-on Manager, right? Okay, so let's see how it works. So let's start here creating something. For instance, we create a circle, and so get the inductance of a circle. So let's make it as a radius 25 millimeters. We need it to be open, so we can create an electromagnetic port if you want on one side. So let's create a circle. That's the basic element upon which we will mount the fast Henry geometry. Then we enable the workbench here. We create a solver element for fast Henry because we want to run a fast Henry simulation for extracting inductance and resistance. The fast solver element here contains all the high-level parameters for the simulation. You can understand what I mean by looking into the documentation of fast Henry. That's a precondition, knowing how fast Henry works to understand what you need to fill up here. But trust me, if you want, I'm just inserting some parameters. You can see anyway, you can quickly understand some of them. So that's the minimum frequency for the simulation, the maximum frequency of the simulation, the units, and so on and so forth. Then we need to define a fast Henry geometry. We would use the circle as a basic, if you want to shape a basic path for a series of segments, which are the main blocks that are used for fast Henry simulation. So let's create something which follows the path. In this case, a circle. You can see that actually we only have 3 segments because by definition the path has a discretization in 3 segments. We can make them 20, for instance, or I don't know, 10, whatever you want. Okay, so let's start with 20. So that resembles actually a circle. Okay. You will see there are some red dots, which are the nodes that are connecting the different segments together. Also in the path here, we'll see each of the segment has a certain height and a certain width. Okay, now we need to create a port, an electromagnetic port. That's where we actually inject the signal, inject the current. So let's select the first and the last node, and we can create a port. So we see this small arrow, which is the electromagnetic port. So all set. Here we can also define in the solver the folder in which the workbench would create the file, and so we can export and create the file. Okay, so we finish exporting. We have the file. We can have a look at the file. Here, that's the fast Henry input file with the name we defined. So you can see we have a nice text file that's actually representing the structure we defined in the workbench. So we can simulate that structure within fast Henry. So starting with fast Henry, let's run a simulation here. So we get the same file, okay, and run it. Okay, and you get the results here. So you can see that a frequency 1 Hertz, the inductance is actually 1.7 minus 7 Henrys. So that means that actually we have 171 nanohenry here for the structure. Is this correct? Okay, we can have a quick check for that one as well. Okay, let's follow some very old, if you want, but very valid formula. So we're taking the formula here from this bulletin from the NIST, and that's actually the very well-known Kirchhoff's formula. So let's take, if you want, an Excel file already prepared for you. So the formula we're going to use is this one. You may remember that the radius of the circle was 25 millimeters. The cross-section in this one, because actually we have a square cross-section here. The segment is a parallelepiped, and so we have an equivalent radius. And you will see that the inductance actually is 1.73, let's say, Henry. So where's the difference? Okay, it's very small, but there's a difference. So you may argue why. Okay, let's try to refine the discretization here, because you remember this is not actually really a circle. Okay, so let's make it, if you want, more discretized. Let's go 40. Okay, so that's actually much better in terms of discretization. You can see it's very easy now to change the geometry since you have the workbench. So let's export again, overwrite the previous file. So now we can run a simulation and see the result. And so now you see that we are quite close to the result that we get from the analytical formula. Okay, let me open it up. Okay, 72.9, 72.3. Okay, so it's quite close. You may also appreciate that going up with the frequency, the inductance lowers. That's correct because of the skin effect. So you can see that the simulator is able to represent, if you want correctly, the behavior over frequency. What else? Okay, that's for the fast-Henry solver. As we mentioned, we also can support Vox-Henry, which is a solver which is based on voxels. So let me show you how it works. It is very similar to, if you want, a fast-Henry, but the basic shape is a voxel. So let's create a part, in this case, a 3D part, just like a torus, for instance. Okay, and then we switch to the workbench again, and then we create a Vox-Henry simulation, Vox-Henry solver element. So you can see again, we have the file name, folder, okay, the other parameters, and maximum, minimum frequency, and so on and so forth. And then we can actually assign this one as a conductor. Okay, so first of all, we'll do, this one becomes a conductor. The torus, okay, is a conductor. Okay, this one is a dummy one. Okay, so you may see that now we have a block here. That's because voxelization will, in principle, take time if the discretization is very fine. And so we want to avoid that one. We just represent, if you want, the space in that taken by the torus. Okay, so you can see it inside. We want to discretize it to see how the voxel looks like. So we can voxelize the conductor here with this option. And we still don't see the voxel. We see it's voxelized true, but we want also to show voxels. So voxels is false, so let's turn it to true. And now we see the voxelized conductor. So you can recognize quite well, if you want, a kind of Minecraft-like structure. So that's the structure we can simulate by using Vox-Henry. Okay, just as a sake of an example. Okay, well, now we're approaching, if you want, the last part of the presentation. Let me return to the slides here. So what's coming next? First of all, we would like to integrate fast solvers control within the workbench. What does it mean? You have seen that now I launched the simulation from outside the workbench. So we just created the file, and then we can launch with external solver the simulation. It will be very nice to be able to launch the simulation from within the workbench, show the log and the results, and even visualize the results. So for instance, for the capacitance, you may have the charge densities. Today, this requires fast model, which is actually another tool we distribute, but only for Windows. Is a kind of oldish, if you want, and was born to allow also 3D modeling. Actually never made it, so we left it to the, if you want, real-time visualization of the text file describing the geometry. And it's very good if you want for visualizing the geometry. So let's make a very simple example here with fast model. We can open the fast-Henry file that we had before created. Okay, so we have it. You see that the keywords are even colored, and then you can see here actually the coil. Okay, but that's not for modeling, it's just visualization. Okay, so you can check if your input file is correct within fast model. Next is extending the electromagnetic workbench for full support of also the other solver we distribute. So faster cap and fast cap for capacitance and fast imp for the higher frequency. We're seeking sponsorship in that respect because, of course, if anybody is willing to provide help in that respect, we'll be happy and glad to accept it. The same was done for the electromagnetic workbench for Fast Henry, with a company sponsoring the development, and actually you can see the results. We also intend to complete the support for Vox Henry because as of today, the voxelization relies on some slow brute force algorithm. Of course, there are much better algorithms which are well known, if you want, but it was a prototype, so with no intention to be the best and fastest algorithm. You may also know that freecad at the moment is not very good in handling voxels itself. Okay, that's all another topic, but actually you need some level of development here to keep it fast enough within the workbench. And of course, for all those parts, we are seeking any kind of sponsorship of development in the open source community, meaning that everything we do has the intent to be open source and stay open source. So we're, I won't say against, but we are very much in favor of the open source. And so with this one is all. So I thank you very much for having followed our presentation and hope to get in contact with you soon.